Hello everyone. In this video, let us try to look into the basic clock tree algorithm, and we call it as H tree algorithm. So this will help us to understand some of the quality check parameters that we looked in the previous videos. That will give a more practical approach to those particular quality check parameters. So let us start with H tree before moving into any of the advanced concepts of clock tree algorithm. So let us start with the basic H tree algorithm. So for example, we have this chip over here. We have the square chip over here. Usually when you see a chip, it is usually a square shape or a rectangular shape. For example, for our case, we'll take a square chip over here. And the purpose, and we have like 16 clock pins over here. So each and every dot represents a flop over here, and each and every dot represents the clock pin of the flop. So you have the 16 flops which is sitting at this particular points, and the clock pins are located at this, and the clock pins of those flops are located at this black or at this white spots. So this white spots, each and every white spots will be the clock endpoints for which we need to connect. Also, the example that we have taken now over here is the clock pins are sitting very periodically, are very equally spaced over here. So the distance from each and every clock pin from the other one is same. So we are taking this basic example, we are taking this simple example to understand some advanced concepts of clock tree. So let us try to understand the basic clock tree algorithm. The purpose that we have, the purpose of this particular tree is to make sure that this clock reaches to this each and every clock endpoints in such a way that it fulfills all the quality check parameters that we have been learning in the past videos. So that is the purpose, that is the whole agenda of learning the clock tree, of agenda of running the basic H tree algorithm. So let us try to start connecting this particular clock in a different fashion. So there could be a way where we could just take this clock signal out and connect it in this way. We can take this out and we can connect it this way. But there is some way that we need to try to connect it, because we have to meet the quality check parameters. So let us try to do this. So the first step that we'll be doing is we'll take this whole chip. So it's a top down approach. It's a divide and rule approach. So we'll divide everything into small pieces and then try to capture and then try to capture it. So the first step will be to divide this complete chip into two halves. So we'll be taking this particular center point, or this particular center line, and we'll be dividing the chip into two halves in this direction. So we will be having two halves over here like this. So we'll have this one complete half with us, and we'll be having this complete half with us. Since there are 16 clock endpoints that we need to connect to, we can't take a direct approach. We have to move step by step. So the first step will be to cover this particular half, to divide this particular chip into this half and this half. So we have divided into two halves. Next, what we'll do is, so since we have two halves with us, let us take this half over here and try to break it into even more halves. So we'll try to break this half into, we'll put a line over here and we'll divide into four more halves. So like this. So now we have this one full half, we have this one whole half with us, we have this one, and we have this one. So basically we don't have half, we have quarters. So we have this one quarter or one quadrant, we have this one more quadrant, we have one more quadrant, and we have one more quadrant. Now each quadrant has got 4 clock endpoints. So what we'll do is, let us say for example this quadrant, let us try to break this even into more halves. So we have this one, we'll try to break it into two halves over here. So one will be this half and one will be this half. So let us try to do that. Similar, so this is what we done. We have this one quadrant which is divided into two halves. We have this one more quadrant which is divided into two more halves, which is this one and this one. And similar, we have this half this one and this one. So we have broken down every quadrant into two equal halves. So now let's say, for example, if this particular section, let us try to divide it into even more halves. So like this. So now we have this small section, we have this small square, we have this square, and we have this square with us. Similarly, for this particular quadrant, we have four squares. One is which is placed over here, one is which is placed. So these are all virtual squares. So this is one more square, this is one more square, and this is one more square. So each and every squares has got equal number of clock endpoints. So that's the whole purpose. So even before building a clock tree for millions of flops, we have to make sure that we are dividing the chip into small squares, and each square should have same number of flop. That makes it very easy to connect them. So that's the purpose of. So you can understand how building this small H tree has made us to understand the concepts of building an H tree for advanced or for millions of flops. So millions of flops, you need to divide into small pieces or small squares, and each square or each area should have same number of flop endpoints. So in this case, we have this one square which has got one clock endpoint. We have one more square which has got one clock endpoint. And similarly for other squares also. So now our job is to take this clock pin, take this clock signal from this particular point and connect it. So now we have connected all the clock endpoints with the wire, with this particular piece of wire. And if you see, this particular clock is now reaching at each and every clock endpoint. Now with this particular tree built, let us try to look into some of the quality check parameters. Let us try to start with some of them. So we had listed 6 quality check parameters, and we will start with skew. So skew, as we said, that it was basically the time required for the clock to reach the launch flop, and the time required for the clock to reach the capture flop, and the difference between those time should be exactly 0. In our case, for example, let's say the launch flop is sitting over here, and the capture flop is, let's say, sitting over here. So the purpose of this skew check is to check that whether this clock signal is reaching at this point and this point at exactly the same time. That's what the purpose of skew is. Or in that matter, this clock signal should reach each and every clock endpoint at the same time. So let us try to look into a small example. Let's say the distance between this particular clock and this particular clock endpoint is D1. Let us just call it D1 now, and let us try to call the distance required, distance from this clock pin to this flop clock endpoint as D2. Now if you calculate the distance, so you have from this, but let us try to calculate this distance from clock pin to this point and from clock pin to this point, and let us try to compare them. Okay, so from this clock endpoint, you have this one piece of wire which is common, so it is same. From this point, you have this piece of wire, and you have this piece, so both are same distance, both are same length. Again, it's matching. Now from this point, you have this piece of wire, and from this point you have this piece of wire, so again they are matching. From this point, you have this small piece of wire, and from this point you have this small piece of wire, again which are again of the same length. And from this point you have one more piece over here, and from this point you have one more piece over here, again they are of the same length. So this essentially says us that the clock required to reach this point and to reach this point, since the lengths are equal, so the time required to reach this particular endpoints will be again the same. So over here the skew is exactly 0, because the time difference between the difference between the time required for the clock to reach this point and this point are exactly same. In that matter, the time required for the clock to reach this point, and let's say this point, is again the same. If you calculate the distance and if you test it out as a homework, let's say if the time required for the length of the wires from this clock endpoint to this point, or let's say this point, is exactly the same. So hence we can say that we are beating the skew. But again, there is a catch over here that we'll be looking into. Let's say we'll be looking into that particular catch in the next video. But in this section, for right now, what we have is we have skew which is exactly equal to 0, and we can put a green tick over here, which means we are good to go. But again, unless we are good to go with this from a skew point of view, but we have to check the other quality check parameters to say that okay, we are good to go with the from the clock tree point of view. So we'll be looking into the pulse width check, duty cycle check, all other checks, and see whether we are actually meeting the all other quality checks. And with that, we can, if we are meeting, if there is a green tick for all of them, we can say yes, we are good to go with this clock tree. But and the points which we are not meeting, we will be putting a red tick over here or a red cross over here, which will say that okay, we are not meeting, so we have to do something about that. So for now, from this point of view, from a skew point of view, we are exactly meeting. And what we'll do, since I'm running out of time, in the next video we'll be looking into the pulse width check, and also we'll be looking into a catch. So there is a catch over here which is not quite evident from this particular slide or from this particular diagram. It will be evident maybe in the upcoming slide. So let us try to look at the catch and the look and the all other quality check parameters in the next video. Thank you.